Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. So I talk about several different topics in this course. If you remember, I started talking about carbocation, then carbon ion, carbene in nitrogen chemistry, followed by some of the benzene chemistry, organolithium, organomagnesium, so organometallic chemistry, and the phosphorus, sulfur, silicon, so the p block elements, and also about the organoboron chemistry. So in the following classes, so I'll think there will be 5 or 6 classes. So I'm going to talk about some of the question answer which came in the different type of NET, GATE, and JAM exam, because that can also make sure that you understand the material which I cover, and also help you to prepare for those competitive exam. Okay, so let's start with some of the questions. So first question came in the NET exam. So you can see the question which is saying give the correct order for the rate of thermal decarboxylation of the following compounds. So this is given, this is A, B and C, and now they are asking the thermal decarboxylation reaction. So that means what we are talking, that you will have this corresponding carboxylic acid which is going to get out from here. So once the carboxylic acid is going to get out, what you are end up generating? You are end up generating a corresponding carbon ion. So from here, if you see the CO2 is getting out, you are generating a, and once from here the CO2 will be out, okay, let's write the mechanism. I think if you have not followed, try to understand how the decarboxylation reaction happens. So generally, if you see the decarboxylation reaction happens by you need to use some sort of a base that will form the minus. Now you can come back here, and so this can allow you to get minus CO2, and you generate this corresponding anion. Okay, so here you are going to form. So this is, you can see, this is next to pyridine. And here you are generating, this is also pyridine, but so now we have to compare them. So that means to predict the correct order for the rate of decarboxylation, you have to understand the rate of decarboxylation depends on the stability of this. After the decarboxylation, once you form this corresponding carbon ion, you have to understand the stability. So if you try to compare them, one of the important factor here, once you have this type of benzylic carbon ion, okay, versus this aryl carbon ion, what are the effect which is important here? So you can clearly see in this particular compound, we can able to draw the resonance structure. We can able to clearly draw the resonance structure, but here we can see clearly the only effect is the minus I effect, and then here you don't have that. So what we are seeing, the resonance effect. So resonance will be again, the resonance will have a better, the more stronger effect compared to the inductive effect. So that's why you can see the C will be decarboxylating much faster compared to B, compared to A. So the correct order will be the A is C greater than B greater than A. Moving to the next questions. Again, I think the question which is asked, if you have this epoxide and you treat it with BF3 thread. If you remember, I talked in the class that BF3 thread is actually a Lewis acid, correct? So now if you take a Lewis acid, and again this question came in the NET 2019. So what will be the product? If you remember, I think we talk about this thing in the class, that once you have epoxide and you take a Lewis acid, it's going to form a plus, and then that is going to open the epoxide to generate a you'll be able to generate some sort of a species like that, where there will be plus and there will be O with a Lewis acid. Okay, So now in this particular substrates, if you again the Lewis acid which is a BF3 going to bind here, and if the epoxide going to open up, there is a two different possibility. It can either open up through this way, so that means let me try to draw them. So here you can clearly see that these are the methyls which are now it can open up a epoxide this way to form a plus and O with Lewis acid, or it can able to form the other one where it can form a plus here and methyl. So now the question comes, if you try to compare it, this is a, you can see this is a tertiary carbocation, this is a secondary carbocation. So if you learn about the stability of carbocation, we always talk about the tertiary will be more stable because of the number of hyperconjugation. Correct? So here then if that is the things, then this will be the corresponding intermediate which is going to form. Once that is going to form, the formation happen. So this is the proton from here which is going to be. So now you are forming a plus charge there. Once you are forming a plus charge, we cannot draw them like up and down. We should not draw them. I think we should draw like a straight line here. Let me erase. I think by mistakenly I erase everything. I think. So let me just draw them. So what I was trying to show you that, so here you have a methyl, correct, plus, and you have, because once you form a carbocation, now you kind of lost the corresponding stereochemistry, so you have this O with a La. Okay. So now you can see that, so there will be a proton going to be, there will be proton abstraction going to happen, because to neutralize the positive charge. So this can give electron density. The sigma bond of carbon hydrogen can give electron density here. So that can form this and then it is going to end up forming and now what is going to happen, you can think about this as a some sort of a enolate. Okay, so this can come back and take a proton. So if you see there is a two methyl here, now both are in the same side will not be a favorable structure. So that's why when the protonation will be happen, the protonation will be happen from the top phase, so that the product which is going to form which will be trans. Okay. So that means if you see that, then we end up to a product here. This is the one which is the answer A. Okay. The other answer, if you try to see, these are this is not even possible. Clearly there is no possibility of that particular methyl to migrate there. So what they are saying that there is a possibility, they are saying if this methyl is going to migrate here to form this carbocation here, and then there is a possibility they are saying like here, if it is going through formation of carbocation, like a methyl is migrating here to, so these are not the correct answer. The correct answer will be A here. In this question, predict the major product A and B formed in the following reactions. So we talk about this dithion chemistry. If you remember, we talk about how do you form this, how do you form this corresponding dithion from this SH, and then you have here you are using this corresponding formaldehyde, correct. Now once you if you remember in the class in the sulfur chemistry I mentioned that clearly that once you use so these are the protons are the acidic proton here. So once you use a base like butyl lithium, they can able to form the corresponding carbon ion here. So that carbon ion can able to participate in a SN2 reaction. Also I talk about that, and also it can take part in a epoxide opening and other reaction as well. So here what is happening in first reaction, you can see here you have a primary alkyl halide and you have a corresponding epoxide. So here I think as you can see these compounds can take part in the SN2 substrate, and this is a very good SN2. This is the corresponding bromide, primary alkyl bromide. It will take part in a SN2 reaction. So if it is go for SN2, what will happen here? So let me try to use a eraser. So let's try to see the product going to form. So what is going to happen? It is going to take part in the SN2 reaction, and then what they are doing, they are treating with AgCl2. If you remember, we use AgCl2 to to remove the dithion and get back to the corresponding aldehyde. So if this will happening, then you will be getting back to the, so this will be your product in this. So B will be, this is the B. So let's look for the products where the B is given. You can see B is given here. This is the product we are asking. So in this option number A and option number C, this is the B is given. So let's try to solve the answer for A. So here you have a epoxide versus a secondary chloride. Again you see the chloride is not a beta leaving group, not good for SN2. So that's why this this corresponding carbon ion will be taking part opening of the epoxide. So once this opening of epoxide going to happen, what is going to happen? There is a chloride here, and you open up the epoxide, formation of the O minus, and you have this corresponding So now you can see clearly this O minus will be taking part in another SN2 to get rid of the chlorine here. Which is going to form this compound, okay. And after that, once you use AgCl2, you remember AgCl2 going to deprotonate this dithion and form the corresponding aldehyde. So that means you end up forming this corresponding aldehyde here. So you can see this is the structure we are finding in the option number D and option number A, having this structure which you are getting in the product. So now if you see option number A having both the correct answer for A and B. So option A will be the correct answer. So let's go to the next problem. So here I think the problem is given that we start with 1 chloro, 1 phenyl, propane 2-one. So let's try to draw them. So we are talking about propane 2-one. So this is a propane and there is a 2 position carbonyl. We are talking about 1 chloro, 1 phenyl versus we are talking about a 1 chloro 3 phenyl. So now they are saying if you treat them with a sodium methoxide, you end up giving same product A. So what will happen if you treat with sodium methoxide here? If you remember, I talk about a reaction using alpha halo. So these are alpha halocarbonyl compound. If you remember, alpha halocarbonyl compound treated with a base. Now I am talking about a carbon ion chemistry. So in the carbon ion chemistry, you have learned that this can take this proton, form a carbon ion. It can attack here, get rid of chlorine to form this. So this can give you to the very important rearrangement reaction called Favorsky rearrangement. So you will be forming this intermediate. Now if you treat here also, sodium methoxide, what is going to happen? This is going to abstract this proton from next to the chlorine. This will be more acidic proton. It's going to take the proton next to the phenyl, and then it is going to attack here, because chlorine is a very good leaving group, so it is going to form the very similar intermediate here. So you can see both are forming very similar intermediate. Now what is the next step of the Febrovsky reaction? The sodium methoxide is going to, the OMe minus going to attack here to the cyclopropane. This can come back, is going to form the corresponding ester there with a CH2 minus pH, which can take a proton to get to the corresponding product. Okay. So that's why the both of these going to end up forming this same intermediate for the Febrovsky and then end up forming the product, same product. So now if you try to, now we have to find out the name for this compound. So it's saying methyl 3-phenyl propenoate or methyl. So if you see, this is a, actually this is a propenoate, correct? If you give carbon number 1, 2 and 3. So this is a 3-phenyl, but of course there is, so this is a methyl propenoate. So that means a methyl 3-phenyl propenoate will be the correct answer. It cannot be methyl 2-phenyl, because the phenyl will be in the terminal position, not in the internal position. What is the major product P and Q from the reaction given below? Again, this came in the GATE exam. So what is happening here? We have given two different compound here, and you are treating with the corresponding silver oxide. So now we try to learn about this chemistry. What is happening here? So you have this methyl in the equatorial position, bromine in the axial position, and now if you treat with silver, what is going to happen? Silver with the secondary bromide is slowly started forming a bond with the silver and bromine, and this carbon bromine bond going to get weak, and it's slowly going to develop a carbocationic current. So if that is happening, then if you remember that generally if you have a carbocation formation happening here, then so then to stabilize that, this is the sigma bond can give electron density. Okay. So that means what is going to happen here, if you forming a corresponding carbocation here, forming a carbocation here, then so this is the bond which is the anti-periplanar to this, so they can, the CH going to, this can end up forming you to the corresponding cyclohexanone, correct? So we clearly understand this will be the product. If you start with the, so this will be the product here, first one, and let's try to show this will be the P. So you can understand the P will be this one. Okay. Now let's try to figure out the what will be the structure for the Q. Now the question comes, once, so this bromine was in the axial, now question comes, in the same substrate, if the bromine will be in the equatorial, what will happen? Again, you can think about here also, the silver is going to form a bond here, correct? Now for the, and then that is going to generate some sort of a delta plus character. So if you see that these are the bonds, like, So these carbon-carbon bonds and these carbon-bromine bonds are anti-periplanar to each other. So what will happen here, this bond, sigma bond electron density will be given here to allow this carbon-bromine bond to get out. That can end up formation of, you can think about, so this bond is going to attach here, here it will going to, it is going to form a OH with a positive charge, and we have a methyl here. So this will end up forming a 5-member ring with a methyl group, and again you can see clearly that the methyl is up and you have a corresponding CHO which is going to form here. Let me see. Yeah, so this will be your, actually this will be your axial bond here. So let me just go back and fix it. So what is going to happen once you form this one? Now you can clearly see that this bond going to give electron densities to this anti-bonding orbital of this carbon-bromine bond. So this can allow formation of this compound here. So this will happen in the same site, but here there will be a positive charge here on this carbon. And this can able to, so this oxygen lone pair can give electron density, can convert to the corresponding aldehyde. So you can see this will be the correct answer for the Q. The product obtained in the following solubility reaction again came in the GATE exam. So you started with the enantiomerically pure compounds, and they are asking that if you treat sodium acetate and acetic acid, you end up forming a, 2 acetate group here. There are 4 options. One, they are saying a racemic mixture of trans 1,2 diacetoxycyclohexane, or enantiomerically pure trans, or the racemic cis, or a mixture of cis and trans. So what will be the correct answer here? So let's try to draw them first. We are talking about a 1,2 disubstituted. Now if you think about drawing them like both of them are, so you have a OTS here, and then you have a O acetate here. Now you can think about from there, once they are in the both are in the equatorial, they cannot do anything, any reactivity here. You cannot. But once you go for a ring flip, again you will be seeing that and draw this. So now your OS will be here, and you will have a your OTS. So we can also we can switch them also. I think that way it will be better. We can write OTS here, and that can help us to understand the question even better. You have OTS here, and then you have a O acetate. So now once they are in the diaxial position, of course that will not be the most stable one. So you will see the equilibrium will be always in this side. Okay. But once their axial position, now you can expect some sort of a neighboring group participation. Now this oxygen lone pair can attack here to get rid of the OTS group. So once that is happening, so you started with a a enantiomerically pure compound, so it's a trans, and now you can see here that let me try to draw the next step. So you are forming some sort of oxonium here. Yeah, sometimes it's very difficult to deal with this, because of the I think I can try to redraw them. The shapes are not looking great. Yeah, so now if you think about, there is a formation of oxonium, correct? And so both of these oxygen, because it is getting rid of the OTS group. Now if you try to think about this one, what is the structure actually? This is, both of them are up, and there is a plus on the oxygen, correct? So now if you think about this particular intermediate which is forming here after the NGP happening, now you can clearly see that this particular intermediate, this particular double bond kind of on the two on actually it is both the oxygen actually sharing these charges. So you can think about this can have a sigma plane which is passing through this. Okay. Now if the nucleophile can attack, suppose now what is going to happen, you have a sodium acetate, correct? Now if you have a sodium acetate attacking from this side and this side, suppose it is attacking from A, from this side, attacking from here is B, you end up forming a compound. Let's try to draw them. If this is the A, then what is happening, there is SN2 happening, correct? So both cases you are seeing SN2, then you will be so this is via A, and once you are attacking via B, so what we are seeing that at the end what you are forming, A and B, they are enantiomer to each other. So you actually there is a 50-50 probability attacking from the either side. That's why you end up forming a racemic mixture of the trans compound. So the option 1 will be the correct answer. Correct order for the stability of the following carbocation is, again here we are talking about stability of A versus B versus C. Now let's try to understand what is the so these are talking about the carbocation, correct? Now if you talk about this particular carbocation, there are CH3, and there is a CH2. So there are total 8 hyperconjugation can be, so there are that many CH bonds are there that can take part. Here you have only 6 proton can take part in the hyperconjugation, and then here you have a 6. So if you look into that, then you might be thinking that A will be more stable on the basis of hyperconjugation, but you are missing something else, that there is a oxygen O methoxy. So that non-bonding orbital can be donated to the empty p orbital here. So this non-bonding orbital donation is going to stabilize this one way more compared to this hyperconjugation. And then there is one more effect in the B, which is this is a allylic So these are called allylic carbocation. If you have allylic carbocation, this can be resonance stabilized as well. So you can try to draw them like this, that it can come here to go stabilization. So there is a resonance stabilization for B. In case of C, you are seeing the very important stabilizing factor is the non-bonding electron is given to the vacant p orbital. So that's why the C will be way more stable compared to B and compared to A, which has only the hyperconjugation. So that's why the answer will be D. Major product in the following reaction is, once you see a carbonyl compound NH2O is acetyl chloride, you can think about the Beckmann fragmentation or Beckmann rearrangement. So now what is going to happen here, let's try to see. From the product we can clearly understand there is a CN here, and CN formation happen only from the Beckmann fragmentation. That means first thing is, and again if you remember, the Beckmann fragmentation only happen at the time when you have a stable carbocation formation possibility. So first thing, formation of the reaction of hydroxylamine with the ketone will generate the NOH, which will react with the acetyl chloride to form OAC, correct. So now you can see there is you generally what you are seeing here, that if there is a possibility of a carbocation generation which is stabilized, then it will go for that route instead of the Beckmann rearrangement. So that's why this bond going to get clipped to get rid of the OAC, that will generate the corresponding CN and a carbocation here. And of course I think we missed the methyl group here. So there is a methyl here. So means you are generating a corresponding tertiary carbocation. So after that what is going to happen, there will be a proton abstraction going to happen from here to neutralize the corresponding carbocation. That will end up you to this product. Okay. So if you try to give them a numbering here, if you have this methyl is 1, 2, 3 and then 4 and 5. So this is the 5 and then this is the 4, 3, 2 and 1. So this will be your correct structure. So here the option A will be the correct structure, okay, not the option B or the option C. Because here one of the things you might be thinking, sir, why not happening from the methyl? Because if it is happening from the methyl, you will be here you are generating a tri-substituted olefin, correct? But here you will be generating a exocyclic one with just a olefin which will be a di-substituted one. Like here it is a terminal in this side, there will be only H here, correct? So and then there will be two substitution in this side, correct? So here I think this will be way more stabilized one compared to this one. That's why this will go for hydrogen abstraction from the internal position. For the 4 reaction given below, the rates of the reaction will vary. So they have given the order, they have actually arranged them in the highest versus the lowest. So if you compare between 1 and 2 versus 3 and then compare between 3 and 4. Let's try to compare between 1 and 2. So if you see from the starting material to product, it is clearly understandable that some sort of a nucleophilic attack happening from the O minus, some sort of a nucleophilic aromatic substitution type reaction happening for formation of and formation of a species like this. And then what is going to happen? This is going to come back and it is going to break this carbon nitrogen bond. Okay, once it is going to break the carbon nitrogen bond, it is going to get you to the corresponding product. So now you can clearly understand, if this is the reaction it is happening, then this negative charge is going to be more stabilized if there is a nitro group there. So that's why the 1 will be reacting faster compared to 2. That was correct. Let's try to understand about 3 and 4. So again 3 and 4, there is a different type of reaction is given. I think we have learned about some sort of a non-classical carbocation. When I talk about the carbocation, that part I talk about this. And also I talk about very similar example during that time. Now they are taking there is a aromatic group with a nitro here, which will be electron withdrawing, and you have a OTS. So what is happening again, once you have a olefin here, the pi density can give electron to this corresponding sigma star orbital to get rid of the, so the OTS can be out from here. And now once the OTS, after the OTS is gone, it is as you use the pi cloud, so that can the pi bond, so that can able to generate. So there could be a bond between here and here. There will be plus charge here, or could be a possibility that it can form a bond between these and these carbon and form a positive charge there. Okay. So generally what people do, you can write this, instead of that people generally write this as a 3 center 2 electron bond. Okay, so you can write a delta plus here. You can think about the positive charge is actually around these 3 carbon. Okay, so now if there is a positive charge here, if you have a aromatic ring with a nitro group, that positive charge will be destabilized. Correct. So that's why if you don't have the nitro group, then that will be reacting faster compared to one with the nitro group. So despite having the nitro group, this will be reacting slower. So that means in this case the 4 will be reacting, 4 reaction, the reaction of this particular reaction of compound 4 will be faster compared to the 3. So we want to look for the option the 4 greater than 3. So the D will be the correct option here. Correct order for the rate constant for the following reaction, it will be very similar. I think here what is happening, you can see the nitrogen is attacking here, going for some sort of ipso substitution here. For that you can understand that the Z, so they are giving 3 different group here, CF3, CH3 versus OCH3. So of course what you want here, you want some sort of electron withdrawing group, so that once the nucleophile is going to attack, that will generate an anion here, that anion can be stabilized. So for that you want Z equal to electron withdrawing group, that means CF3 will be reacting faster compared to the CH3 and compared to the OCH3. So this will be the order for this reaction. So you can see the option A will be the correct option. It is very similar to the previous problems. The major product formed in the following reaction. So here we can see these are a alpha halocarbonyl compound, but there is 2 different halogens here. If treated with sodium methoxide, so we know that this could be a problem for the Febrovsky rearrangement. So what is going to happen here? Now you can see one side there is no proton, other side there is a sodium methoxide can able to generate this carbon ion, which can attack here to form this sort of intermediate. Let's try to draw the intermediate here. So you will form the corresponding cyclopropane, where one side we have a dimethyl and one side we will have a Br. So sodium methoxide going to open up here. There is a Br here. So you can see this is going to come back here, and this is going to generate one negative charge next to the methyl. So this will be generating a minus. We allow the elimination to happen to get to the corresponding product. Okay. So if you look for this is the C will be the correct option here. Okay, so thank you so much, and I hope you guys have learned some of the problems of this carbocation and the carbon chemistry. And thank you so much, and I hope you will come back to the next class. Thank you.